All right, so it looks like it's 12 o'clock now. We'll give everyone one more minute and then we'll get started.
Good.
All right, so it's 12:01, so let's get started. Thank you all for joining our webinar on Scratch measurements. I'm Abby Lindberg. I lead GelSight's applications engineering team. So anything kind of customer support, training, application development comes through myself and my team. I just wanted to start with a couple reminders. We're going to be recording this webinar. It's already recording, and we're going to post it to YouTube after. Once it's all uploaded, we'll send an email out with the link to watch. Also, another reminder to use the Q&A feature throughout the webinar. We'll answer questions as we go. We have Frank Chang from my team, who's based in the Bay Area. He'll be answering the Q&A via the chat throughout the presentation, and we'll also answer some questions at the end. So with that, I'll pass it over to Thierry to introduce himself and get the webinar started.
Yeah, thank you very much, Abby. I'm Thierry Mantel, so I'm in charge of the global distribution of GelSight, as well as some key accounts, especially in the aerospace industry. Since before joining GelSight, I spent a long time in the aerospace industry, and before that, also in the automotive industry. So thank you, Abby, and welcome, and thank you for all the participants to this webinar. It's a very good opportunity for us to illustrate one of the most common usage of GelSight portable scanners, which is the measurement of scratches and dents. Scratches and dents occurs, during the lifetime of a product, and it's almost unavoidable from the early stages of the manufacturing process of this product and during its entire existence. We have all bad experience of scratches, dents, impacts on the doors of our cars or on the windshield of our cars, and I'm sure you have all experienced this kind of thing. And it's in our personal life, but in your professional life, scratch and dents can represent also a very important aspect. And these scratch and dents may have two consequences for your product. Just an aesthetic one, which will lead to the decrease of the perceived value of your product, and also a functional one, which is also very critical for during which the performances and also the lifetime of the product can be seriously affected by the existence of these scratches. So this is typically the case, in the aerospace industry or also in the power generation industry, where a minor surface defect can have very serious consequences. And in both cases, it needs to be considered with a particular attention. The characterization of scratches is also not very easy. We have seen many customers having tremendous difficulties to characterize some scratches on shiny surfaces, on transparent material, needing to take molds, which is time consuming and very costly. And there is, at the end of the day, issues with the accuracy and repeatability of the measure. So in the demonstrations, Abby will propose you in a couple of minutes. GelSight will bring you a unique way to measure these scratch, and dents in a very accurate and repeatable way, and on any kind of geometries and material. And this is really one of the strengths of the GelSight. So enough talking now, and just place to the demonstration with Abby.
All right, thank you, Thierry. Let me just stop sharing this cover slide here, and I'll share my GelSight software. And before we get into the scanning of the samples that I have here, I'll talk a little bit about how GelSight works. So let me just share my screen. Let's go here. All right, so we should be able to see that now. And to start with a little bit about how GelSight works, we have our Series 2 system here, and it has a gel sensor on the end of it. And basically we have a camera and a lens and an illumination system in here. And when we click the button on the probe, we're actually taking 6 images, one with each one of these banks of LEDs illuminated. And we take those 6 different images with 6 different lighting orientations to get 3D data from that. So I just installing the gel cartridge back onto the probe here. And the gel is what's going to conform to the surface that we press it onto. You'll see I'll just press my fingertip into the top of the gel here, and you'll see my fingertip show up on the screen. So now we'll get into some of the samples that I've brought to scan and measure scratches and defects on. And the first one that we'll start with will be the edge of this blade. Let me put this on front of our video here. So I've got a defect along the edge of this that I can barely feel with my fingertip here with my fingernail. And we'll start with the offset function, which is going to be great for defects on edges. So I'll just go ahead and take the scan of this. I'm just going to press the gel onto that surface. And I clicked the button to take the scan. And our 3D data is generating. And then we'll be able to open that scan and take a look at it. I'll actually jump over to channel 1. This is going to be the view that is with the first illumination bank turned on. So we can actually see all 6 of those illumination channels in our software by selecting the different channels here. The first thing we like to do is look at this surface in 3D. So I'll click on the 3D button here, and we can see the reconstruction of that surface. Now I'll actually increase the scaling too. This doesn't change any of our measurement data, but it can help you see some smaller features better. So we can really see that defect on the edge of this blade here. Now I'll jump back over to our analysis page. And we're going to talk about the offset function. So I'm going to select offset from my list here. And the input for the offset function is going to be 1 line. I'm just going to draw a line through my defect. So I'll just draw a line like this. And we can see the profile pop up at the bottom. Now, this is a handheld tool. I might not be perpendicular to the surface. So the next thing I'm going to do is just define what my reference surface is. So to do that, I'm just going to add 2 levels here, 1 on either side. And I'm going to configure those to just be my reference surface. So I wouldn't want to put it in my defect. I just want to put it where my reference surface is. And then I have my measurement regions. So we'll expand this one. Maybe we want to compare the average of our reference surface to the minimum point along the profile. So I'll go ahead and select minimum here. So now the offset that's being reported in the top corner here, it's a little over 100 micron, is going to be the difference in height from the average of the reference surface to the deepest point on the profile, or the deepest point on our defect on that edge. Now from there, we can just turn this into a PDF report. So I'll just go ahead and click PDF. And now we can customize our report. And we can zoom in, maybe want to zoom in on that defect there and customize how we want to view that. So you see taking the scan to performing the measurement, pretty quick process with the GelSite software. And the next function that we'll talk about is really going to cover measuring defects over an area. So with this function, I like to say offset for edges because it's really great for measuring depth along a line. But we have some other functions that'll give us the deepest point over an area. So that's what we'll talk about next. So I'll get back over to our capture page. And what we're going to look at next, I have this elbow joint here. And we've got, I mean, there's a bunch of scratches on this, but we'll look at one of the specific scratches. So I'll just come in here and I'll take the probe and press it onto the surface here. So we can see all of those defects there. Maybe we'll focus on that one in the middle. And I just click the button to take that scan. And now we'll go open that one. And we can see that surface. And let's look at this one in 3D as well, just to kind of show the curvature of that elbow joint. Got this one here. And next, let's talk about the scratch function, and we'll measure the defect let's take a look at this one here. So for the scratch function, I'll just select it on my list here. And the scratch is going to give us the deepest point in an area. So the first thing that I'll do is draw one shape around the scratch itself. Something like this. Click the check mark. And then one around the scratch and some of the normal surface. So maybe something like this. And I'll click the check mark again. And now I can select Analyze. And the output of the scratch function is going to be the deepest point within the scratch and the tallest point within the scratch. So you can see the blue dot, about 30 or so micron below the reference surface, and the red dot, which is about 35 above the reference surface. So the blue dot is going to give us, that negative scratch area. And then we'll also be able to measure a burr height with this function as well. And the scratch function works on all types of surfaces. So we can look at flat surfaces, curved surfaces, and complex surfaces like the elbow joint that we were just looking at here. No settings changes between those. So you'll see basically it takes the data from what's outside of the first shape and inside of the second one to define that reference surface. Now, if we look at this elbow joint again, there's still going to be some places that GelSight can't access. So even though we have a portable handheld system, we're going to be able to access many other locations than some other measurement tools might have access to. But if I wanted to measure a scratch in the corner of this elbow, I'm still not going to be able to access it with this Series 2 system here. So in that case, we do like to use a replica material. So before this, I actually made a replica just of the scratches here. We use a metrology grade replica putty. I just applied some to this area here. And I took it off, and we're actually going to scan this directly to measure a defect on here. So let me go back to capture. And there's a couple defects on this as well, but we'll look at a specific one. And I'm just going to take a scan directly of the replica material. And I click the button to take the scan. Now, once that generates, we'll open it up and let's go look at this 3D so we can look at the shape of the replica. So we'll go to 3D here, and you can see as a replica of that pipe shape, we've got a scratch on it that now looks like a raised feature, right? Because we took a mold of a scratch. So now we're looking at a raised feature on the replica. That might not be as intuitive when you're measuring a scratch that now you've taken a mold. So now you're looking at a raised feature. So we do have a workflow for that. We have the option to invert and transform our 3D data so that it looks like the surface of the part again. So I'll go ahead and I'll click this triangle button here, and it's going to tell me it's going to generate a new height map. And as that generates, you'll see the next one will look more like the curvature of the pipe. So we can see that defect here now. And now let's go over to our analysis tools, and let's use our scratch function here and measure the depth of this defect. So I'll click on scratch again, and maybe this time we'll just go in with a rectangle and another one here. And I'll rotate that one a little bit, maybe this one too. And we'll click Analyze. So we can see the blue dot here is our deepest point, and the red dot would be the tallest point in that defect on the replica. So for those locations that even GelSight still can't access, we've done a bunch of studies supporting different replica materials that are compatible with our system. So we talked about offset for defects along edges and scratch for defects over areas. Now, I will talk about our defect detection function next, and that's going to show us how to automate some of our scratch measurements. So let me jump over to capture again. And for this example, I've got an airplane window. So we have a bunch of defects on this window, a bunch of scattered ones over here. And we'll take a look at those. Let me put this in the field of view here. Now, the defect detection function is great for, right now, it's for flat surfaces. But you might say, hey, well, this window actually has some curvature to it. I'll hold it up over here, or I'll hold it up over here too. So we're looking at a field of view of about 14 by 17 millimeters with this system, with the Series 2 system. And, really large curvatures or really large radii might look flat to our system. So even though defect detection is really for flat surfaces, we can still use it on curved surfaces if the radius is large enough. So let me scan one of these defects on here on this transparent material. Kind of another thing to talk about too. We don't care about the optical properties of what we're scanning because of this pigment layer on the gel. So I'll go ahead and I'll take a scan of maybe this defect on the window. All right, let's open that one up. And let's take a look at our defect detection function. So I'm just going to select defect detection on my list. And defect detection can run on the full field of view or on a region of interest. I'll just draw kind of a box in this area. And I'll click Analyze. And the output of defect detection is going to give you all of the characteristics of the deepest defect in your field of view. I'll kind of zoom in on this one here. We can see the length, width, area, volume, and depth of that defect, as well as the profile through the deepest point. You'll see it kind of looks like the offset profile. So we're drawing a line through that blue dot, which is the deepest point in that defect. Now, this function, we just drew one box to define the search region. Whereas when we were doing offset, we really had to draw a line through the defect. And for scratch, we had to draw shapes around the scratch. But for defect detection, we're defining a search region itself. So we can automate this. So let's go. Maybe I'm happy with my configuration here. And I'm going to click on the pencil icon and click Set Defaults. And this is going to make this analysis my default configuration. So this input shape is always going to apply to any defect detection function that I add. You'll see if I click it again, it's going to run the same function. So I'm going to go in and I'm going to add a pass-fail criteria to this. So you might have different tolerances for different parts that you have, and we can go in and enter those into the GelSite mobile software. So I'll click on Analysis at the top, and I have defect detection selected. And if I scroll down, I can select pass-fail. And we can do this to any of our analysis functions for any output that we have on the right-hand side in the output panel. We can select pass-fail for it. So I'll click this checkbox. Maybe we'll say anything under 50 micron is going to be passing. So now, once we've added our pass-fail criteria, let's set up some of that automation. So I'll go over to the capture page again. And from here in the bottom left-hand corner, I can click this window that says Scan. And I'll select the Run a Routine box. And we can see that search region that we defined as part of our routine settings. So now I'll just go ahead and I'll scan some of the other defects that are on this window here. So let's see, we've got a couple other ones. Put that here. And I'll keep scanning them. There's a few in that field of view there. And maybe we'll go back to. All right, so on the right-hand side, we're going to see our green box show up around the passing defects. So this would mean these defects are less than 50 micron. And we've got a red box around the deeper defect that was failing. So I could open up one of these that we just took. And we can see the result from defect detection here. We can see this one was about 44 microns. So this is passing my threshold that I configured. We can also clone these functions too. So maybe you have different pass-fail criteria for different parts. We could have defect detection for part A and defect detection for part B as well to add another layer to automating that for different processes. So far we've talked about offset for edges of defects and scratch for area-based defects on complex geometries and defect detection for defects that we want to automate on flat or mostly flat surfaces. Now, we also have some defects that might take up a larger field of view. So as I mentioned, the field of view of this camera is going to be 14 by 17 millimeters. But what if we want to measure the length of a defect and it's longer than that field of view? So we just released this past year, actually this past software release, the image stitching module of our software for applications like that. So I'm going to go in and I'm going to select stitch, and that's going to take me to that interface here. And for this example, I have, say, 3D printed part here with a scratch on it. So I'm going to go in and I'm going to take scans of this to stitch this defect, this scratch. You can see it show up on my scan here. And I'll click the button to take the scan. Now I'm going to slide the probe over a little bit and take the next scan here. And I'll slide it over a little bit more and take the next scan. And we'll do one more here. And you'll see the green preview pop up when I'm taking the scans. That's basically saying that it thinks it knows where the next scan is going to go and how we're going to stitch it. And once I'm happy with all the scans that I've captured the length of this defect here, I'm going to go ahead and click the save button. And the actual image stitching is happening right now. So what we see at the top is just a preview, and the stitching algorithm is running on the scans right now. One thing that I'll point out, the scratch that we're looking at right now is on a very textured surface. So we can easily have enough features to stitch these images together. Something that might be a scratch on a really smooth surface, like on glass or polished metal, might be harder for the algorithm to stitch without any other features. So in those scenarios, we actually recommend using a blue painter's tape and just take a strip of the tape and put it next to the scratch. And as you take your scans of the scratch, it'll use the texture from the tape to help with the stitching algorithm. So you'll see once my scan has been stitched together, we can go and analyze it. Now I can click on this and I'm just looking at one frame of the stitch right now. And I can use any of our analysis tools on the individual frames that are being stitched. If I go and look at our full stitch scan here, right now we just support 2D and just 2D measurements on this. So we can use our 2D tools or we can use our ruler tool. So I'll actually go and maybe we'll just measure the length of this with our basic ruler function. So I clicked on our ruler and I drew a line across it to measure the length of this defect. I can still go in and look at this in 3D. So let me do that. I'll click on 3D here. And here's the 3D reconstruction of the scratch on that surface. All right, so I'll kind of summarize the analysis functions and what they're for again. So we're doing offset for edges of defects, so grate on the edge of the blade that we covered here. And scratch for complex geometries. So scratch will be your go-to for any kind of curved surface or curved in multiple orientations. And then defect detection will be your automated scratch detection for flat or curved surfaces. And now we can even do image stitching for those scratches that are larger than our field of view. And then handle the actual 3D scratch measurement part on the individual frame basis. So I think with that, I'll hand it back to Thierry. Maybe you can talk a little bit about the value that GelSight brings and maybe how some of this can compare to other measurement systems that we see in the field. And Thierry, you're muted.
Yes, sorry. Thank you very much, Abby, for this very clear demonstration. I think as everybody has seen, you clearly have like a metrology lab between your hands, and one of the large advantage of GelSight is the fact that the lab goes to the part and not the contrary. And in many occasions, we face the company face very busy metrology labs. It takes days, sometimes weeks, to have the answer to the measurement of a scratch, and GelSight has the unique possibility to do a measurement in situ in the factory floor in your hangar. So it's one of the most obvious value of the system. It's fast, it's simple to use. I mean, during the training session we do, people are very quickly able to use the system very efficiently, and it works on any kind of surface. So basically, during this demonstration, Abby selected a blade in steel, in Inconel probably, a pipe in copper, a transparent acrylic for the window, plastic with a 3D printed part. We don't care. We can really do measurement on any kind of surface, and I think this is really unique. There is no other tool which has this ability. After that, doing a measurement also implies the fact that this measurement needs to be accurate, repeatable, and this is the case of GelSight. Most of our customers, they are doing their internal, MSA 1 and 2 type studies to just prove that the system is accurate and repeatable enough to do measurement. And at the end, you have a quantitative data on which you can rely to take decision if you want to scrap the part or if you want to continue to use it. So this is once again the main obvious value I can identify for GelSight. Traceability is very important as well, since the digital nature of the GelSight information can be saved, and you can come back few days later to have a look again to those data. And something we introduced in 3.8, I think, is the possibility to interface GelSight with in your industrial environment, and to give the possibility to communicate between GelSight and your quality management system. So this is really a tool which can be fully integrated in your industrial environment. After that, when we discuss with our customers in terms of challenges to measure, defects and scratches, most of the time, the existing technologies, they are struggling with the optical properties of the surface. Stylus, it's difficult to have access to some location, and you have the information on a single line, nothing else. GelSight propose the information on the surface, and also the use of molds. This is really something which is widely used. Customers are using molds and it's difficult to guarantee the traceability of these kind of processes, and it's definitely not easy. And as I was mentioning, the optical properties of the surface is key. especially when you want to measure, scratch on a windshield, or even on composite material when you have a mixing of resin and carbon fiber. This is typically extremely difficult. Yeah, and I mean, scratch and dents may appear, a little bit a small defect, but this is really very important. If you take, for example, the steel industry using cold rolling processes, the fact to have, a dent or scratch on a regular basis on the plates, of course, it cannot be accepted by their customers working in the appliance, the automotive, or the aerospace industry. And in some other, industries like power generation or aerospace, any scratch or dent can lead to, potentially the initiation of corrosion or a crack. And during the lifetime of the product, it can propagate due to the environment, the thermal environment, or the vibration, fatigue. And it can lead to, difficult situation and potentially a rupture of these components. So I would like to let a little bit time to the question. I have seen that we have few questions on the Q&A session. So maybe it's time now to answer this question, Abby. I don't know, and maybe there will be more coming.
Perfect. Yeah, feel free to add your questions now and we can go through the ones that have been submitted. I've also seen Frank has been answering some of them in the chat here. So I guess we can go down the line and I'll just check the answer live button on a few of them. So the first question we have in here says, how accurate is the scratch function going to be with selecting such a large reference area to the high and low points? So I'll just check answer live. I think that's referring to the scan that we did with the scratch function. I'll just open that up on the shared screen here. Let me go to this one. There we go. So the way that this function is defining the reference surface is it takes what's outside of the first shape, but inside of the second one to define that reference surface. So we actually do want it to be larger than the first shape. I think Frank answered kind of a ratio for that, maybe like 3 or 4 times larger than the first shape, to give us enough data to build the reference surface. So I think we're doing a 4th order form fit to that data to really, define what we're going to be measuring against. So the accuracy for this system specifically is going to be 1 micron plus 4% of the nominal in the Z direction. All right. We can go ahead and answer one of the next ones. All right, Frank's typing on one of them now, so I'll skip that one. Using the defect detection function for a smaller radius. For example, measuring numerous defects in small diameter tubing. So one of the things with the defect detection function is that it's really for those flat surfaces or large radii. I'm not going to talk about in detail today, but we do have our pit detection function, which might be a better fit for this one. Pit detection is really, it's used a lot for corrosion applications, but it's going to give you the characteristics of multiple defects in your field of view. And this function will work on flat surfaces and curved surfaces that are, more cylindrical. So not anything more complex than that, but some curvature will be supported. So definitely look at the pit detection function for those applications. All right. And we've got, what is the maximum length that stitching can be used for? So for this one, it depends. It depends on the computer processing specs that you have. So I think, Thierry, maybe you've gotten the most scans in one stitch out of all of us, right? On just
Even with a Surface Pro 8, I have been able to do stitching with using up to 12 frames, and of course, if you put them all together, you can easily measure a scratch of maybe 50 millimeters, 60 millimeter. This is typically something you can do. I think personally, the maximum I have done is about 48 millimeter on a very long scratch, but there is no reason that you cannot continue, with that adding frames.
Yeah, and that would especially be if you have a more higher powered computer. It does depend on that
Yeah.
too. So if you get a more powerful computer, you can definitely stitch more images in that case too.
Yeah, something is very important to mention is that when you reconstruct a scratch, you will the scratch will look planar. For example, if you have a scratch on a very complex shape like a cylinder or a 3D shaped component, you will not be able to reproduce the mean shape of the component because, of course, the probe when the probe is in contact with a part, you do not know exactly. The probe doesn't know exactly in which orientation it is compared to the part. We are not able to measure the position of the probe in the reference of the part.
All right, so the next question we have is could you confirm if you use the Plastiform P80RA for that negative mold? So yes, I actually did use that specific replica material for this one, the Plastiform P80RA. We have a white paper to share too on the results of using GelSite with that replica material. If you are interested, we can share that. How long does each gel pad last? So this is another it depends question. But basically for aerospace applications, just as a range, looking at defects on metal, scratches on metal parts, we're looking around like 300 scans per gel. But it really depends on the type of surfaces that you're looking at. We have some customers that are getting well over that for their applications. Thierry, if you want to elaborate on any interesting applications you've got with that.
Yeah, we have surprisingly customers working in the abrasive domain able to do up to 400 500 scans. We know that we have ski manufacturers having been able to do the measurement of the roughness of ski bays, doing more than 1,000 scan with the gel, and we also know that some customers they are using the GelSite in very difficult environment, and for them sometimes they need to replace the gel after 50 or 60 scans. It strongly depends on the type of surface and also on the cleanliness of surface. The surface should be dry without oil, this kind of thing, which really will preserve the lifetime of the gel.
Thanks, Thierry. I think kind of related to that too, follow-up question is how does it do with printed metal surfaces? I know you want to talk about this one, so.
Yeah, same thing. We have several customers using GelSite to characterize the 3D printed parts, especially measuring the roughness, because GelSite has the unique ability to measure surface roughness in a very short time. So basically, when these customers have to set up their 3D printed machine, they use GelSite to measure the roughness and just to fine tune their parameters. And same thing, this is really something which is very powerful, and even on metallic surfaces, in 3D printed processes using metallic powder, the gel has a pretty long durability. You just need to clean it on a regular basis with the swabs which are delivered, with the system to remove the dust which can be attached to the membrane.
We've got this is related, so I'll skip to this question. Is it possible the gel of the scanner can be damaged because of usage, and how to prevent that? So the gel is a consumable. You do replace it when it's damaged. So after those 300 or whatever your application will be, you will replace the gel. And just some of those tips that Thierry shared would be the best way to prevent wear on it. So we're just going to clean it. We're going to clean the surface if possible before we take our scans. And then the biggest one would be just not dragging the gel across surfaces. So, we took a scan of the edge of this blade, right? I'm not going to drag it across the surface. I'm just going to press it or even roll onto the surface. But any kind of wear, shear forces are going to wear your gel out faster. All right, we've got another one. When measuring conical point deformation, such as dot peened marks, does the equipment deform all the way to the full depth of the mark? So this is also we're basically looking for an aspect ratio of 1 to 1 to make sure the gel can get to the bottom of a feature. So if you imagine like a very narrow crack that's very deep, the gel is not going to conform to the bottom of that crack. So as long as the dot peen marks are kind of wide enough versus the depth to get to the bottom of, then we should have no problem with that. My experience is the dot peen marks that I've seen in the field, we get to the bottom of them. Thierry, I don't know if you wanted to add anything to that as well.
Yeah. I mean, in terms of accuracy, what is very important, first of all, is really to make sure that the gel is really in contact with all the little structures of your surface. The advantage of gel site is that it's extremely visual. The operator, the user, will see immediately if the gel is really in contact with the surface. You can even on this frame, you can see that there is the cloudy area around the part, and this is typically what you observe when the gel is not in contact with the part, so with the surface. So it's extremely visual, and it's very helpful for the user to make sure that he does a proper scan.
Yeah, I'll demonstrate that to the visual for getting to the bottom of a feature, which is actually a really nice feature of GelSite because you can go back and reference that to make sure that you did make it to the bottom. So I have this other large defect on this pipe. You can see that's a big dent. Right now, I'm not at the bottom of it. You can see it's really smooth. Now I'm at the bottom of it. So I would take the scan now. But that would be your visual indication. It's pretty clear when you're not making contact with a feature. You really do see the feature when you're pressing down hard enough. All right, I think we've got time for maybe 1 or 2 more questions. And I think we probably won't get to all of them, but is the software running on your computer or does it come with a handheld monitor? And what is the interface to the computer? So the software is running on your computer. We typically use the Microsoft Surface tablet, and we like the touchscreen aspect and the portability of it, but it can run on other computers as well. We do have some system requirements. But the probe is connected to that computer via USB-C connection. So there's just one cable that goes to your computer from there. All right, and then when do we anticipate having 3D stitching measurement capabilities? That's a great question. I don't have a timeline for that. But what I will say, I mean, right now you can see the STL file, you can download the STL file, but right now, our system is a single micron accuracy system. So when you're stitching these images together, the challenge is the 3D at those interfaces, right? And we want to have that very accurate system across that too. So I don't know exactly what we're going to be doing going forward for allowing us to do the 3D on that. So right now we just look at the individual frames. So on that scan that I stitched previously, I would just go in each frame and look at the depth on each one.
Yeah, and this is typically something which is on our roadmap in terms of development, and the GelSite software has tremendously evolved, the last years, and it is in our strategy to bring new functionalities and new improvement, in the software. And I'm sure that this is something which will appear, in the next releases of the software. We always continue to improve, our technology.
All right, I think we're at time now. So thank you everybody for joining us today. Once again, we recorded this session, so we'll make sure that gets uploaded and you all get an email. With any further questions from this webinar, feel free to reach out to support@gelsite.com or info@gelsite.com, or just Cherry and myself if you have our emails too. But once again, thank you all for joining.
Thank you, Abby. Thank you to everyone. Thanks for your time.